All right, so here's where we're going to get a little bit more practice with equivalent resistance. We introduced it in the last video, and now we're going to see how to apply it, and we're going to see how to apply it on a larger scale. So let's start off with a relatively simple one, something pretty similar to what we saw last time. So I've got a battery here. Let's start off with maybe one resistor here and another resistor here. Let's say that this is a 300 ohm resistor and this is a 500 ohm resistor. All right, so what I want to do is I want to take this complex, quotation marks, circuit and turn it into a circuit that I'm used to solving. The simple circuit that we can easily apply Ohm's law onto by taking these two resistors and replacing them with one imaginary equivalent resistor. Like I said, I was going to get lazy pretty quickly and my resistors just become squiggly lines. So I've got the green one to denote that it's not a real resistor. It is, however, one that takes the place of these two and acts exactly the same. Since these are in series, our equivalent resistance will be equal to R1 plus R2 plus R3 and so forth, but we've only got the two resistors. So this will be 300 ohm plus 500 ohm. So that gives us a total of 800 ohms. Our equivalent resistance for this circuit will be 800 ohms. All right, hopefully pretty straightforward. Let's up the ante just a little bit. I'm going to erase this one, and let's add one more. All right, let's say that this is a 250 ohm resistor. Now, one of the things that I want to point out on this is, because we're going to start seeing this more and more, imagine all the charges that are moving through our circuit. We can imagine them as coming out of the battery, but remember there are already charges here and all of them are twisting around. But we have charges that come through here, they go through the 300 ohm resistor, and then afterwards they go through the 500 ohm, then through the 250 ohm. That's the second part of what I referenced in trying to understand if it's series or parallel. So even though these are kind of side by side the way that I've drawn them, they're actually still in series. And so we would end up with 300 plus 500 plus 250. That would be 1050. Let's go ahead and throw one more in there. We could put one like this. Another resistor here, and let's say that it's 150 ohm. Great. Once again, while we've got this one kind of side by side with this one, your gut instinct may be to say that they are in parallel. But imagine the current going through it. Current that goes through the 300 must go through the 500 and then through the 250 and then through the 150, which means these are actually all in series. So we'd add them up. This is 800. This is another 400. So we would end up with a total equivalent resistance of 1200. This would be R1 plus R2 plus R3 plus R4. So that's dealing with series. Hopefully that one's pretty straightforward. Let's take a look at a similar case with parallel. So I've got battery, and let's have our 300 ohm resistor, and I'm going to put it in parallel with a 600 ohm resistor. Okay, now on this one, since these are in parallel, now if you were to watch this, let's imagine that we have the current, which is coming out of the positive end of the battery, is going through our circuit, and we've got it going through here. If it goes through the 300, it's going to go straight over here. Now, I mentioned it in the last one, and I'll reiterate. Remember, charges, the current, is always trying to get from the positive side of the battery to the negative side of the battery, which means it's not going to go backwards and get lost and go all over the place, at least for our considerations. The other way to think about this is potential differences act like hills, effectively. This is uphill, and we're rolling downhill until we get to the bottom. That's basically what's happening, and we're going to make more references to that as we move forward. Now, because of that, you have stuff rolling downhill, which makes perfect sense, but if it were to go back this way, then it would have to start rolling uphill, which doesn't make a whole lot of sense. So we've got the charges, whatever goes through the 300, it's no longer going to go through the 600, it's going to go straight over here to the battery. Now, one of the things that I want to bring up is this. You may already be thinking of it. You may have heard of the phrase path of least resistance. We're going to have to deal with that. And while it is pretty true, one of the things that you've got to realize, and we're going to look at this in the next section when we start looking at more complicated parts of the circuit, is that since this has a lower resistance, this is 300 ohms, it does not mean everything is going to go through here and nothing is going to go through the 600. Instead, some of the current goes this way and some of the current goes this way. It will actually split. Now, most of the current will go through the path of least resistance, but depending on what these resistances are, they're actually going to split the current. In fact, no matter what the resistances are, they're pretty much always going to split the current, but depending on how much one is more resistant than another will determine how much current goes through it. More on that later. Let's go ahead and finish this up. 1 over Req is going to be equal to 1 over 300 ohms plus 1 over 600 ohms. Great. We need a common denominator, or you can put this into your calculator. So 1 over Req is going to be equal to 2 over 600 ohms. That's the same thing as 1 over 300 plus 1 over 600 ohms. That'll be 3 over 600 ohms. And remember, this is 1 over our equivalent resistance. So the equivalent resistance on this one would be 600 divided by 3, which is 200 ohms. So if I were to draw this one, it would look like this with my imaginary equivalent resistor. And it would have an equivalent resistance of 200 ohm. All right, so that's with just the two of them. Great. Again, you can solve this with your calculator, or it is useful to be able to do this with fractions, but just a recommendation. Now I'm going to erase this because just like we did last time, I'm going to up the game a little bit. Let's add yet another branch. Let's go with, I don't know, 100 ohms. Great. So this would be plus 1 over 100 ohms. We just keep adding each of them in there. Let's do 50 ohms, plus 1 over 50 ohms. Now I will point out a couple things real quick before I even start solving this. Just a moment ago we had the 300 and the 600, and their equivalent resistance was actually less than both of them, 200. One of the things that I'm going to point out, and this can be very useful on things like the AP exam, if I see this array of resistors and I see that they are in parallel, as I mentioned before, their equivalent resistance must be below any of the individual resistors. So I know that the equivalent resistance of this has got to be less than 50 ohms, because that's the smallest one. Let's find out. Let's see, common denominator is probably still going to be 600, so we've got 2 over 600 ohms, plus 1 over 600 ohms, plus 6 over 600 ohms, plus 12 over 600 ohms. Okay, so I have, this would be 3, 9, that'd be 21 over 600 ohms. We're going to end up with, I'm not certain that that's going to reduce very well. In fact, it can't, because 21 is divisible by 7. That being said, 600 divided by 21, we're going to end up with an equivalent resistance, Req, in this case, is 28.6 ohms. I'm going to go ahead and turn to my calculator. We could call it 600 divided by 21, or what would that be, 200 divided by 7. It doesn't really matter. A lot of times, both I and the AP exam on exam questions will give you ones where you end up with a nice, neat fraction. Though not always. Sometimes I mess up a little bit. That being said, here we go. We also, turning it back from a fraction into an actual value, we find that it is, well, not to say that fractions aren't actual values, but we can see as a number, it is less than 50, just as I said. Now, one of the other things that I'll point out on this is I don't like leaving these in fractional form. You may recall from class, I've pointed out that math teachers insist on you leaving things in 600 divided by 21 because that is the exact value. In physics, we're dealing with real-world values, which means these numbers are only good so long as they're pretty much what matches perfectly. And as we've seen, this is marked as a 100 ohm resistor, but it's probably like 104.3 or 108.9. These numbers are only accurate so far as we know the values that we're putting in there. I never like having 600 divided by 21 because that comes up to 28.57142857. We're claiming way too many significant figures. We're basically claiming a level of precision that we don't have. I emphasize for the purposes of my class that we prefer putting things back in the actual numerical value, non-fraction form. All right. Now that we've taken a look at that, we've looked at some pretty interesting circuits. Let's start going to the true challenge on this. All right, we're going to step this up even more. I'm going to do the following. Let's take what we just set up. I'm going to put a resistor here. Let's say that this is a 100 ohm resistor. I'm going to have it come over here, and we're going to have this branch off into several other resistors. So I'm going to draw this circuit. So I've got 100 ohm. Let's say that this is 100 ohm and 100 ohm. In fact, let's go through and make all of these 100 ohms. I think I've actually got enough for that. We'll find out. I want to find the equivalent resistance of this. Okay, so the thing about this is we've got a complex combination of both series and parallel. In fact, if you track the current, it's going through the entire circuit. Charges are going to move from the positive end of the battery. They're going to go through this. Let's call this RA. This one RB, RC, and RD. Great. Now, on the AP exam, usually when they give you a complex array of these, a lot of times they will all be identical resistors, just like we see here. This is where I'm starting off. However, I am going to give you ones that are non-identical, so you're going to have to be able to work with those. So here we go. As charges move through this resistor, they end up splitting. Some of them go this way and some of them go this way. So the charge that goes through here, the current that goes through A, goes through B, and it goes through C. Some of it will go through B and some of it will go through C. Because of that, A is actually in series with B and C. And then the charges will meet up here and continue going through D to get to the other end of the battery. And therefore, A and D are actually in series as well. Now, the important thing on this is, however, whatever charges go through B will not go through C, because there's no reason for them to try and go backwards. They're being pushed towards the other end of the battery. They're going to continue rolling downhill, as it were, which means B and C are actually in parallel. So now that we've got a complex circuit, what we want to do is the same thing we've done before, break it down into problems we've solved before. We've solved ones that are just two in parallel. So here's what I'm going to do. I'm going to make an equivalent resistance and replace those two with an equivalent resistor that acts exactly the same. So we know this one's 100 ohm and this one's 100 ohm. And I'm going to find the equivalent resistance of these two. Well, that's 1 over 100 plus 1 over 100. We solved that one before, actually. We're going to find that that is going to equal 1 over 50 ohms. It'd be 2 over 100. And so our equivalent resistance, don't forget to invert it, is 50 ohms. Now that I've redrawn it, and I recommend doing this when you're first starting out to get this practice, because otherwise, taking complex circuits, you might get confused. You might be able to do it with just the circle and mark those in, but might be worthwhile doing the redrawing like I do here. So we've got 100, 50, and another 100, and the charges go through all of these. As I mentioned before, these are all now in series, and so I can simply add them together. 100 plus 50 plus another 100. My total equivalent resistance is 250 ohm. Great. Let's see. Let's try and build one of those real quick. I've got the parts here. Let's see what we can do. Let's say that we've got a 3-volt source. Now that I've got this, I'm going to go ahead and turn it into what we know how to solve. I'm going to redraw this one more time. We put these together in series, and we found that our total equivalent resistance was 100 plus 50 plus 100 is 250 ohms. If I have a 3-volt source, then we can apply Ohm's law and predict that 3 divided by 250, we should end up with a current somewhere in the region of 0.012 amp or 12 milliamp. All right, give me just a second. So here's what we're going to do. We're going to get this set up, try and build it in real life. Let's double check our results. So I'm going to plug back in my voltage supply, my regulated power supply, and then I'm going to find some 100 ohm resistors. I'm going to need a few more than I've got out. There we go. And I'm going to try and build this real quick. So here we go. I'm going to pull the 1000 and the 5100 that I still had on there from earlier. So, let's see. I like to imagine it similar to this. Like I said, the snap circuits are good for being able to do that. So we've got one resistor that kind of goes along the top here, and then we've got, let's see, something like this. And I'm going to have these two connect. I think I need another 3. No, that's fine. I'll just use a 4. And then I'm going to have my last 100 ohm back over here. Great. Okay, so we can imagine that there is some more coming off of here and that I could put a power pack over here. And we've got our battery, goes through this resistor, splits off into these 2 resistors, comes back together and goes through this last one. I've actually got this upside down because that's technically the positive, but neither here nor there. I'm going to power it with a regulated power supply just so we get a little more reliable results because my batteries aren't quite at the 3 volts. That's what they are nominally, but when I actually get this powered up, it's usually a little off. So let's check here. So I'm going to connect this one here and this one here, connecting our circuit, and I've got my meter here. We're expecting something in the ballpark of 12 milliamp, so I'm actually going to adjust it to the milliamp setting so that we can read that. Let's see what we get. The result is 11.03, so we got about 11 milliamps. Why are we off a little bit? Well, take a look at some of the previous videos. While these are marked 100 ohms, some of them might be 105, some of them might be 95. And as a result, our real-life values are going to be a little bit off. That being said, we can predict the current, or at least very close to the current that's going to be going through it. Like I said, this is using the equivalent resistance and drawing conclusions based off of it with Ohm's law, and we can see that it does, in fact, match real life. All right. I'm going to disconnect this. I'll leave this out. We may actually try a few more of these. In fact, I want to go to an even more complex one. So what we've got here is we've got 4 resistors in a complex combination of both series and parallel. So let's try this a little bit more challenging. Because you can expect for the purposes of my class that you will be solving circuits that have these many components. In fact, I think I usually max them out at about 6 resistors. Usually 5, though sometimes I've been known to give you 6. So here's what we're going to do. Let's draw another one. And do that. I'll split this over here. I'm going to put 1 down in here, and I'm going to put 2 over here. I like to work my way around. We'll call this RA. This one will be RB, RC, RD, and RE. Great. Let's go with A. Let's call it 100 ohms. Let's go with RB. Let's call it 1,000 ohms. Let's call RC 100 ohms. RD 100 ohms, and RE 5,100 ohms. Because I've got a few of those resistors, let's go ahead and use those values and see what we come up with. Now this one's a lot more complex. What I need to do is I need to start breaking this down into things that I've seen before. Well, I've seen one resistor in parallel with another, although there are 2 here. So let's quickly look through. So imagine that we've got charges moving through our circuit. Ones that come out of the battery are going to go through A, and then they split off. Some of them go here, here, and here through these branches. Whatever goes through A will end up going through either B or C or D. So A is actually in series with B, C, and D. Whatever goes through B is not going to go through C or D or E, so this is in parallel with C and D and E. Now, you'll get used to this with a little bit of practice, but our smallest part is probably going to be right here. We've got 2 in series. So what I'm going to do is I'm going to replace that. I'm going to redraw this. You do not need to redraw this every time, but I would recommend doing it at the beginning because it makes it easier to follow along with, at least I feel. So since these are in series, I'm not even going to write it down. We know that we can just add them directly together, so we get an equivalent resistance of 5,200 ohms. Great. And then we've got another one that is 100 ohms. And then over here, we've got 1,000 ohms. And then back up here, we've got 100. Great. Now we've got this, which are 3 resistors that are each in parallel with one another. I know how to deal with that. So I can then do 1 over 1,000 plus 1 over 100 plus 1 over 5,200. Now, this is a great instance in which I'm going to jump straight to the calculator. You are welcome to work with fractions on this. I recommend being able to work with the fractions and using them when they're easy, but feel free to ignore them when they are harder. Plus 1 divided by 100 plus 1 divided by 5,200. Now, I got an incredibly tiny number. Remember, this is equal to 1 over the equivalent resistance. So you got to invert this. You got to take 1 divided by that value at the end, and we find that Req for all three of these in parallel is 89.3 ohms. I'm going to bring this up again. 1,000, 100, 5,200. Our smallest one is 100, and our equivalent resistance is less than that. You will always see that happen. Great. Now I can get this finished up. We've got the following. It looks like this. And I've got an equivalent resistor right here. That's 89.3 ohms. And we've got 100 ohms back over here. And so our total equivalent resistance, I guess I'll draw it here. Total equivalent resistance is going to be 189.3 ohms. We might just want to call that 190 because, yeah, I'm not certain that we know this that closely. We've got a 3-volt supply, because I keep using a 3-volt. You know what? I have been using 3-volt an awful lot. Let's bump that up. Let's go up to a 6-volt. 6-volt supply. Oh, wait. Actually, just so I'm certain that I'm not damaging anything, let's go with a 4.5 volt. That's what... So these components were designed to be used with a 3-volt supply. That's why I keep using it. Okay, so 4.5 volts divided by 189.3, and we should get something like a current of 0.0238 amp, which is 23.8 milliamp. I need to adjust the setting on my meter because it maxes out at 20 milliamp. All right, let's test this one real quick, and then we'll do one more, and that should hopefully be the practice that you need. Okay, let's see. I think I might actually be able to build this. Ooh, here, not quite actually. Let's see. Okay, so let's do this the easy way. 100 ohm in the middle, not that it makes much of a big difference. 1,000 ohm on the left-hand side, and we need a 5,100 ohm. Oop. Right here, and we want a 100 ohm here. We want another 100 ohm right here. And I need to start connecting these up. Okay, I think I'm going to need some more 2s. Ooh, I'm also going to need a 1. Like I said, it helps if you get used to working with these so that you can get through them much faster. All right, here we go. Oh, I need that one there. Let's see, so here's a 2, here's a 2, and I'm going to need a couple of 5s to go along with this. Great. I've got some 6s. 4. Hey, there's a 5. There we go. So now we've got our circuit. We've got the 100 ohm comes in here, and then it splits off into 3 branches, 1,000 ohms, 100 ohms, 100 ohms, and a 5,100 ohm. And then they all come back together at the end, and they're going to go back over to the battery. Like I said, hopefully you're able to follow along with this just fine. I really do like these snap circuit kits because they make it very easy to recreate exactly what you see on the page. So I'm going to connect these here and here, because that's where my wires would connect. And we've set it to 4.5 volts. I'm going to turn on my meter, and here we go. The measurement I get is 22.2 milliamp. We predicted 23.8, we got 22.2. Again, we're a little bit off on that. These are not going to be perfectly the values that they're marked. We could turn back around and be able to better note those if we took measurements on exactly what they were. But for the most part, this is good enough because then we can make certain that we get the right amount of power to something, which is the point of a resistor. All right, let's see. Let's take a look at one more. The nice thing about the equivalent resistance ones is you can actually make up your own circuit. As long as you just put in all the resistances, you'll be able to work through it and find out what's going on. All right, here we go. Let's go with one here, 2 here. That looks good. 1 here, and then 1 here. Let's go with some different values here. Let's go with a 50 ohm resistor. Let's call this a 100 ohm. We'll call this one a 25 ohm. Maybe this one will be a 75 ohm. And this one will be a, I don't know, let's just do 100. We're probably going to end up with some strange numbers here. Let's go with a 200 ohm resistor out here. Okay, so this one's a bit more of a mess. That being said, we're looking for the smallest part of the circuit. Now, one of the things that I'll point out, and this is partly from me being a lot more used to it, we're going to have charges as they move through the circuit, the ones that come out of the battery. Some of them will go to the right and go through this mess, and some of them will continue going through this. This resistor is kind of off by itself, which means it's in parallel with the entire rest of the circuit. So we can't do anything with it until we deal with the rest of the circuit. So if I look back in, you're going to find that it's very similar to last time. We can redo this. I'm going to try and draw it smaller because we're going to need a lot of room here. Okay, so here's 200 ohms, here's 25 ohms, here's 50 ohms, here's 100, and we get an equivalent resistance for these two in series of 175 ohms. Great. Now these two are in parallel, and I could go through. I know how to deal with them. So I'm going to combine them using 1 over. So I've got the 50, and I'm going to replace both of those with what they are equal to. Okay, so this one's 200, this one's 100, and this one's 50. I can now combine these two, and I get 1 over 25, 1 divided by 25, plus 1 divided by 175, and then I take the reciprocal of that, and we end up with 21.9 ohm, at least a 3 significant figure. Okay, sorry about that. I've been in the room talking to myself for a minute or two. You can see that I've kind of cut ahead here. My camera, the way that it works, it cuts out after a certain amount of recording, just kind of by default. Jumped ahead a little bit. You probably saw me stopping somewhere in here when the video cut off. I'm going to see where I'm going to splice this in. But we took these two in series. They added together to be 175. These two were then in parallel. I added them reciprocally and found that their equivalent resistance was 21.9 ohms. You'll notice it is less than the 25 ohms, so it is still less than either or any of the resistors in the parallel. And then you will end up with these three in series, so 50 plus 21.9 plus 100 should get you 171.9. And then these two are in parallel, so we add them reciprocally and get 92.4. Okay, so that's running through. Hopefully that isn't too much confusion, but that's basically what we showed there. And this is applying equivalent resistance on more complex circuits. Take a look at the homework and a couple of other things, although honestly, if you want some additional practice, just sit down and you can make up your own circuit. Now you can do that if you're filling in all the resistances. Soon enough, we're going to start taking a look at circuits that we don't know all the resistances of, and therefore those can get a lot trickier. But hopefully, this is a good example of how you can work with equivalent resistance to take a complex circuit and break it down to the simple circuit that we are used to solving. Here in the immediate future, we're going to start looking at the individual components in each of these big circuits, so it isn't just knowing things about the total circuit, but knowing what's happening in all the individual parts that we're going to take a look at next.